for example, their definition, their different kinds. And in the next chapters, we will explain about the details of each topic. For example, a special kind of integral equations or Fredholm integral equations, and in chapter 2 we will explain the details of this kind of integral equations, for example, when they came from, and actually different types of Fredholm integral equation. And we will continue the discussion in chapter 3 about another special kind of integral equation named as Volterra integral equations. And also we will have the details of this kind of integral equations. Another kind of equations that are very important for us are Fredholm integral differential equations and also Volterra integral differential equations. These two kinds actually that we will define today include both integral and derivative of the unknown function. We will continue our discussion in chapter 6 with singular integral equations that are a special class of integral equations, and we work on their kernel, and we will discuss that which kernels will give us singular integral equations. And also we have non-linear integral equations including Fredholm and Volterra. And if we have time for this semester because of the delay for starting the classes, you know, for Iranian students, actually we passed 1 month of the semester, and you unfortunately because of the problem for system lost this 1 month, and I hope we can complete this course until the end of the semester. Okay, let us to the first chapter that give us the total definition and important preliminaries of integral equations. As you can see here, first of all, we have the definition of an integral equation. Can you tell me, before starting the lecture, actually, can you tell me what what a differential equation is? We call this equation a differential equations because, as you can see, we have the derivative of the unknown function in this equation. You can see that here we have the first order derivative, and here also we have the second order derivative of our unknown function. You can see here that the function y is a function which is dependent on the independent variable x. So here we have y prime of x plus x, the second order derivative of y with respect to x, equal to 0. I'm sure that you know many different kinds of differential equations and you have seen them in different courses. As I said, in differential equations, the derivative of the unknown function appears, but in an integral equation, as we can understand from the name of this kind of equation, the integral of the unknown function appears. Here in this equation, as you can see here, we have an equation. We have actually an integral equation. The unknown function is the function u. You have the unknown function u in the left side, and in the right side we have f of x plus the integral of k of x and t times u of t dt, t from alpha x to beta x. As you can see, the unknown function u appears in the left side and also in the right side in the integral sign. So we have the integral of the unknown function, and because of this reason we call this kind of equations as integral equation. In this equation, the function f and the function k are given functions. Actually, we know the function f and k, but we are supposed to solve this equation somehow. The unknown function u is determined. So the aim of solving this equation is giving the function u. The function k, which we can see in the integral sign, and it is a multiplication of the function u, is called the kernel of this equation. So this word is very important in the topic of integral equation. So we have the function f as our given function and also the function k as the kernel of this integral equation. And as I said, here you can see in the bond of the integral, let me clear the page. In the bond of the integral, you have the functions alpha and beta. Okay, I was saying that the bonds of integral, as you can see, are given here as functions of the independent variable x. So alpha of x and beta of x are also given functions. Actually, we know the relation of alpha and beta. So as I think you understood, we have to solve this equation and compute the function u. This equation is linear because the function u in the left side and in the right side appeared in a linear form. For example, you don't have the powers of the function u, for example u squared of x, or you don't have sine of u. You just have the linear form of u, and because of this we call this kind of integral as linear integral equations. Here you can see an example. You have the initial value problem. U prime of x equals 2 times x times u of x for all x greater than or equal to 0. And also we have the initial condition u of 0 equals 1. In the next chapters we can see that an integral equation can be transformed to an ordinary differential equation, and also we can rewrite an ordinary differential equation as an integral equation. Actually, they can be transferred to each other. Here, here. So we have our differential equation as we can see here, and also the initial condition. You know that all differential equations together with initial conditions are called initial value problem. So if we say initial value problem, we mean a differential equation together with some initial conditions. And because here we have the first order of derivative of the function u, we just need one initial condition. You know that if the derivative of the function u was of order 2, how many initial conditions were needed? Can you tell me? Suppose that we have the second order. Instead of u prime, we have the second order derivative of u. How many initial conditions are needed in this case? Can you tell me?
2x.
What, Mr. Mazar? 2x? No.
2xu.
No. I asked you, instead of the first order derivative, if I had the second order derivative, can you tell me the number of initial conditions that are needed to have a unique solution for this equation? Here you have the first derivative and also one initial condition. If you have the second order derivative, you have the two initial conditions. I mean u of 0 and also u prime of 0 should be given as initial conditions. Understand? So you can understand that if the derivative order is 3, you need 3 initial conditions. So the number of initial conditions for having a unique solution for a differential equation of order n, if you have the nth order derivative of the function u, you need n initial conditions. This equation can be easily solved by using the method of separation. I don't know if you remember the method of separation or not. In method of separation, we try to separate our variables. You can see that our variables, if we see the function u as an independent function and we don't consider the independent variable x, we can write u prime of x over u of x equals to 2 times x. Actually, we separate our functions. We put all functions in terms of x in the right side and we keep all functions in terms of u in the left side. By taking the integral from both sides, we can obtain the solution of this initial value problem. So the solution is u of x equals e to the power x2. Did you understand? Is it clear? What we have instead of beta of x? Compare this equation with the definition. We have x here, don't we? Instead of beta of x, we have x. Instead of k of x and t, I put s here, but you can consider t. There is no difference because this is a variable, and whatever you want you can name it. So instead of k of x and t, we have 2t times ut dt. I explained that this initial value problem is equivalent to this integral equation. So you easily saw that we could transform a given differential equation to an integral equation. Reversely, we can transform this integral equation to the differential equation or initial value problem that this integral came from. For example, if you take derivative from the both sides, you will have u prime of x here. The first derivative of 1 equals to 0, and this integral you have to use a special formula called Cauchy formula for taking integral from the integral part. Actually, for taking derivative of the integral part, and you will obtain the exactly this initial value problem for that integral equation. So both of them are easily transformed to each other. The initial value problem is transformed to this integral equation by integrating, and this integral equation is transformed to the this initial value problem by taking derivative of both sides. Okay, let's go to the classification of linear integral equations. As I said, we call an integral equation as a linear integral equation if the unknown function u appears in a linear form. So we can't have the powers of the function u, we can't have any other expression in terms of u except in this form, just u. Outside of the integral and inside in the integral sign. So if it is u squared, it is not acceptable. Or if it is cosine of u, it is not acceptable as a linear integral equation. And whatever except u of x. These 6 numbers, actually these 6 types are the different types of integral equation. The first case is Fredholm integral equations. We will explain about the details of each kind in the next chapters. The second type are Volterra integral equations. The next type are integral differential equations. We can recognize from the name of this kind of equations that this class actually include both integral and derivative of the unknown function. For example, you can have u prime of x. So this is the derivative of the unknown function equals f of x plus the integral of t u of t dt. In the right side you have the integral of the unknown function, in the left side you have the derivative. So we call these kind of equations as integral differential equations. The next type is singular integral equations. In singular integral equations we deal with the kernel of the integral equations. Actually, it's very important for us that this kernel is given in which form. For example, if we have 1 over x minus t, you know that whenever t equals x, so we will have 0 in the denominator and the expression will be indefinite. So indefinite. In such cases, we will have kernel as a singular function, and we call these classes of integral equation as singular integral equations. We will discuss about them by more details in the related chapters. The next class or a type of integral equations are Volterra-Fredholm integral equations. If you compare this name with the two first names, you can see that in this case we have the mix of the first case and second case. In the first case we had Fredholm integral equations, in the second case we have Volterra integral equations, and in this case we have Volterra-Fredholm integral equations. And we can see further that if we have the both Fredholm and Volterra in one equation, we call them Volterra-Fredholm integral equations. The next class is Volterra-Fredholm integral differential equations. So you can see the mixture of case 1, case 2, case 3 and case 5. So in your equation you have derivative and integral of the unknown function, and also the type of integration will be Fredholm and Volterra. Volterra and Fredholm refer to the upper bound and lower bound of the integration, and we can see that if both of them are fixed numbers, not functions of the independent variable x, we call them Fredholm, and if they are variable, we call them Volterra. Well, let's go to the different kinds by details and give the general form of these equations. The first case or first class includes Fredholm linear integral equations. For all of them, we also have the nonlinear case, and we will discuss about nonlinear case as I reviewed in the table of contents. We will have them in a special chapter, and we will discuss about the nonlinear cases in one separate chapter. The standard form of Fredholm linear integral equations, where the limits of integration a and b are constants. So until now we know that in Fredholm integral equations the upper and the lower bound of the integral are fixed number. They are not functions of the variable x. So in the general form we have phi of x, u of x equals f of x plus lambda times the integral of k u from a to b, and the linearity can be seen from this linear form and this linear form that we can see outside and inside the integral. The Fredholm form can be recognized using the lower and upper bound, a to b. These are fixed numbers, so we call them Fredholm linear integral equations. In this equation, the functions phi, f, and k are given functions. Actually, you know the form of these functions. The only function which is unknown is u, and you have to solve this problem or this equation to find the unknown function u. This lambda is a constant, and you know that if lambda equals 0, we won't have this integral part. Actually, this part will be deleted. So the necessary condition is that lambda is not equal to 0 and lambda is a fixed coefficient. Okay. Depending on the values of the function phi, we have two different kinds of Fredholm integral equations. We have actually Fredholm integral equations of the first kind and Fredholm integral equations of the second kind. How we can recognize these two different types? In the first case, when the function phi equals 0, you know that this equation will be written as this equation. So the left side will be equal to 0. We don't have this side, and we only have f of x plus lambda, the integral of ku from a to b equals 0. We call this kind of equations as Fredholm integral equation of the first kind. So the function phi determines first kind and second kind integral equation. In the first kind, we have phi equals 0, and in the second kind, in general, this function phi can be any non-zero function, but here we have a special type. Actually, if you have any non-zero function of x, you can call them Fredholm integral equation of the second kind, but here the author considered just one case, and it is when phi of x equals 1. If you replace this value in the general form, you have u of x equals f of x plus this part. We call them Fredholm integral equation of the second kind. Okay, let's go to the next class of integral equations, which we call them ultra-linear integral equations. As you saw, in Fredholm integral equations, the bounds of integration are fixed numbers. But here, we have variable upper or lower bound. The examples or general form that you can see in this book are special cases actually, but in general you can have the function alpha and beta, which both are functions of the independent variable x, or you can have the lower bound as fixed number and the upper bound as variable function, or the lower bound as variable function and the upper bound a fixed number. In all of these cases, we call them ultra-integral equations. But here, the book considered the standard form of ultra-linear integral equations, and this standard form is how you can see here. Once again, we have the multiplication of the functions phi and the unknown function u equals f of x plus this integral sign, and the lower bound of the integral is a fixed number, and the upper bound is x, which is our variable. So we can consider different cases for the function phi once again, and classify the Volterra integral equation as first kind and second kind. Here the unknown function is u, and the function phi, f and k are given, and lambda is the fixed parameter, or the parameter that we multiply by our integral part. As I said, we have these two different cases when phi of x equals 0, which leads to this integral equation f of x plus lambda, the integral of ku from a to x equals 0. We call this kind of integral equation as the Volterra integral equation of the first kind, and in the second kind we have the case that phi of x equals 1, and you can simply check the standard form with this when we replaced phi of x equals 1. So we have u of x equals f of x plus lambda times the integral of ku d from a to x, and we call them Volterra integral equations of the second kind. So in general, the difference between first kind and second kind integral equations in both cases Fredholm and Volterra is that in the first kind we just have the unknown function in the integral sign, just in the integral sign, but in the second kind we have the unknown function both in the integral sign and outside the integral sign. So this is the difference between first kind and second kind integral equations. There are some remarks that refers to the different kinds of integral equations, which they were numbered from number 7 to number 12. Let me bring the first equation in this list. Where is the number 7? Here. The general standard form of Fredholm integral equation, first kind, second kind, general form of Volterra integral equation, first kind and second kind of Volterra integral equation. If you consider these equations, you can see these actually remarks. The first one is the structure of Fredholm and Volterra equations. In the both equations, the unknown function u appears linearly only under the integral sign in linear Fredholm and Volterra integral equations of the first kind. So as I said before, we don't have the unknown function u outside the integral. And the unknown function u of x appears linearly inside the integral sign, because we are talking about the linear case only up to now. We will discuss about the nonlinear case in the next discussions. And the second remark refers to the limits of integration. In Fredholm integral equations, the integral is taken over a finite interval with fixed limits of integration. But in Volterra integral equations, at least one limit of the range of integration is a variable, and the upper limit is the most commonly used with a variable limit. In the second part, actually it says that you can have in the Volterra integral equations, let me bring the general case, you can have both of them variable or one of them variable. In the literature, mostly they consider only the upper bound as variable, but as I said, all of them are called Volterra integral equations. If you have the lower bound or upper bound or both of them. The third remark is related to the origins of integral equations. It means that we want to know that Fredholm or Volterra integral equations are coming from which kind of actually application. It is important to note that integral equations arise in engineering, physics, chemistry, and biology problems. You can refer to these two references to see the details and see that which phenomena can be formulated or modeled as integral equation. And also integral equations arise as representation forms of differential equations. As we saw in an example before, you saw that we transformed this actually differential equation u prime of x equals 2x u of x to an equivalent integral equation. So they can come from a differential equation, or they are somehow the transformed form of the ordinary differential equations. The last remark refers to the linearity property. As it was explained before, the unknown function u of x in Fredholm and Volterra integral equations in the general form occurs to the first power wherever it exists. It means that in the left side or in the right side in the integral sign, wherever you have the function u, you have only the linear form of this unknown function. However, nonlinear Fredholm and Volterra integral equations arise if u of x is replaced by a nonlinear function in terms of u. For example, you have u squared of x, u cube of x, e to the power u of x, or any other nonlinear functions of u of x. For example, here we want to recognize which one of them are linear and which one of them are nonlinear. In the first case, can you tell me if this is linear or nonlinear? For answering this question, you have to check the form of appearing of the function u. Can you tell me if it is linear or nonlinear? Why?
Not linear.
Yeah. Yeah, exactly. Since here we have linear u, but in the right side, in the integral sign, we have power 2 of the function u, and it makes this equation as a non-linear integral equation. In the second example, can you tell me if it is linear or nonlinear? Linear?
Yeah.
Why?
Non-square or 3 power.
But the function e to the power
Yes,
u
yes,
is
yeah.
nonlinear. Okay?
Okay.
Okay?
Yes.
So the second case is also nonlinear because we don't have the simple form of u. If it was linear, we should have here just instead of this function we should have u of t. And in the third example, the last example, we also have non-linear equation, because once again you can see that okay, the left side for all of them are linear, but in the right side, in the integral sign, actually we have non-linear functions in terms of the unknown function u, and in the last case we have sine of u of t, which makes this equation as a non-linear integral equation. Now let me give an example of linear case. For example, you have this equation as the linear integral equation, u of x equals x to the power 2 plus 2 times sine of x plus integral of t u of t dt. First of all, this is a linear integral equation because u here and in the integral sign was appeared linearly. Can you tell me if this is Volterra or Fredholm? The type Volterra or Fredholm, which kind is this? This is linear, okay? It's linear, okay? I want to ask you, can you tell me the classification of this integral equation, if it is Fredholm or Volterra? Which kind is this?
It's Volterra.
What?
It's Volterra.
Volterra, exactly. Because as you can see, one limit of integration is variable, okay? So thank you, Muhammad. So it's Volterra integral equation. Here the whole expression that I circled is f of x. I replaced a special example for the function f. So this is a linear Volterra integral equation of the first or second kind. Can you tell me about first or second kind? Being first or second kind? Is this first or second kind? Exactly, thank you. This is second kind because we have u of x inside the integral and also outside the integral. If we didn't have this part, or we had 0 here, it was first kind. But since we have here and also in the integral sign we have second kind, so generally this equation is a linear Volterra integral equation of the second kind, the classification that we learned until now. Linear Volterra integral equation of the second kind. In the number of remarks or more, I thought that just 4 remarks we have. The next remark is related to the homogeneity property. It's completely different from whatever we said until now. It refers to the situation of the function f. We have 2 different situations for the function f. One, f of x equals 0, and another one is not equal to 0. If we set f of x equals 0 in Fredholm or Volterra integral equation of the second kind, given by the equation numbers 9 and 12, the resulting equation is called a homogeneous integral equation. And in the other cases, I mean when f of x is not 0, then we have non-homogeneous or inhomogeneous integral equation. Let me give an example from homogeneous and non-homogeneous integral equation. For example, here we have, let me write it in a more clear place. Here we have u of x equals the integral of from 0 to 2 t squared u of t dt. Okay, let me ask you some question. Can you tell me if this is a Volterra integral equation or Fredholm integral equation?
No. It's Fredholm, I think.
What?
I think it's Fredholm.
Yes, exactly. Yes, exactly. Since the lower bound and upper bound are both fixed numbers, we have Fredholm integral equation. For being Volterra, we should have at least one of them variable, and here you don't have any of them variable. The lower bound is 0, the upper bound is 2, both of them are fixed determined number, so we call it Fredholm integral equation. This is linear, yeah? Here you have linear form and here you have linear form. Is this first kind or second kind?
Second kind, I think.
Exactly, second kind, because we have outside and inside the integral sign. This is second kind. But about being homogeneous or inhomogeneous, can you tell me which kind is this? Homogeneous, exactly, thank you.
It's homogeneous.
Yeah, exactly. Since f of x equals 0, so we have homogeneous integral equation. So totally we can say that this is a homogeneous Fredholm integral equation of the second kind. This is the classification of this equation. And the next remark is on the singularity or the singular behavior of the integral equation. An integral equation is called singular if the integration is improper. It means that, for example, let me write, if you have, for example, one of the bounds of the integration as infinity. Here you have negative infinity. Here you have, for example, a fixed number a. Or I put b because it's more suitable to the upper bound. Or you have the integral from a to positive infinity. Or we have the kernel of integration, the function k, which is called the kernel of integral equation, somehow that it gives an improper value. For example, if we have 1 over x minus t to the power 3. You know that in the case that t equals x, we will have 0 here, and this value will be improper. So these 3 different cases determine that if our integral equation is singular or not. This usually occurs if the interval of integration is infinite, as I explained to you, or if the kernel becomes unbounded, for example in this case, at one or more points of the interval of consideration. For example, if we consider the interval of integration from a to b. Singular integral equations will be defined later. Actually, we defined it, but we will explain about them with more details in the next topic. But we should know that the methods to handle singular integral equations will be completely introduced in chapter 6. In fact, you can't use the methods that will be introduced for solving Fredholm integral equations or Volterra integral equations in the non-singular case, and these kind of equations need special methods for themselves. So you can't use any method for solving them. Actually, solving this kind of equations is a little difficult, and there are some problem with solving them, and we have to choose a good method or suitable method for solving them that are different from the methods that we use for the non-singular integral equations. The next part is related to the integral differential equations, and as I said before, in integral differential equations you can see both derivative and integral of the unknown function. For example, here you can see 3 different examples for integral differential equations. In the first example, the differential part is given by the second derivative of the function u, and the integral part is given by this integral. So since we have the derivative and integral of the unknown function, we have an integral differential equations. And pay attention to this matter that since we have derivative, for solving this equation we need initial conditions. If we don't have initial conditions, the solution won't be unique. So for solving it uniquely, we need initial conditions. And as I said before, the number of initial conditions are determined by the order of derivative. Since the order of derivative is 2, we need 2 initial conditions. In the second example, we have the first order derivative of the unknown function u in the left side, and also we have the function f, negative sine of x minus 1. And here, this is a typo. Here you have minus and plus. One of them should be considered. Actually, you have to delete one negative or this positive sign. You can't have both of them together. And once again, since the order of derivative is 1, we need one initial condition to solve this problem uniquely. And in the last example, we have once again first order derivative of the function u here. So we need one initial condition. And also we have the integral of the unknown function, so we have an integral differential equation. To recognize that if they are Volterra or Fredholm, we have to pay attention to the limits of integration. For example, here in the first case, can you tell me if it is Volterra or Fredholm? The first example. Let me tell you something to remember the actually Fredholm or Volterra. Okay, the word Fredholm. Yes, it's Fredholm. The word Fredholm is started with F. Am I right?
Okay.
F is the first letter of fixed. Yeah.
X fixed. Okay.
Fixed. So when you say Fredholm, it means that the bonds of integration are fixed numbers.
Yes, exactly.
And if you say Volterra, Volterra is started with V. And it's similar to variable. Variable also is started with V. When you say Volterra, it refers that at least one of the limits of integration are variable. So you can easily recognize that if an integral equation is Fredholm or Volterra. Fredholm fixed, Volterra variable. And you can see here that equations number 16 and 17 are Volterra integral differential equations, and number 18 is a Fredholm integral differential equation.